Okay, so to overview the lab here, basically I have the rough shapes of what your graph should have gotten, whether they were major or minor. The way you could tell the difference between like a major impact and a minor impact is that the major impact, when you compare the first period to the last period, was a couple times greater towards the end or a couple times smaller towards the end. It had a huge impact on, in terms of the amount, in terms of time. Um, the minor impact was probably a 10% difference between the start and the end. None obviously had no impact. So for the pendulum, the length and the gravitational field were your major impacts. The mass did not impact it, and your minor was the angle. For your um, spring mass system, it was the mass and the spring constant, which were your major impacts, and the amplitude, which was none. Okay, part three, the oscillating spring mass system. So for this, we had to look at the motion between the two amplitudes. Your equilibrium point here would be position zero. And we had to look at the forces exerted when the spring was fully stretched at one, and the force of the spring pulls the cart to the left, and compressed at five, and that force of the spring pushes to the right. As you go closer to the equilibrium point, the force of the spring diminishes. It still stretches at two and is compressed at four. And in the middle, there is no stretch or compress, which means there is no net force. The motion diagram, it gets faster as it goes through the equilibrium point and then slows down, stops and turns around at the amplitude, and head backs in the opposite direction. That motion, since it's frictionless, goes on and on. So when you look at the graphs here, um, and we look at position one, it is at its maximum amplitude. As it goes to the equilibrium point at position three, the graph goes to zero. Then at five, it goes to the negative amplitude. As it oscillates back to three, the position is zero, and then one is at its maximum amplitude again. So the velocity is a little bit different. If you look at the motion diagram here, we can see initially the velocity is slow to not moving at the amplitude and increases going to the left. So that velocity is going to be negative at the start from 1 to 3 and getting larger. Then it's still going to left but slows down. So we'll go back up to 5, and then it will increase velocity through the equilibrium point to the right again, and then stop, slow down, and stop back at the amplitude. The acceleration, if we look at the unbalanced forces, the acceleration at the positive amplitude is pulling to the left. That's going to be the maximum force going to the left, which means the acceleration is going to be at a maximum value too. That acceleration is going to drop to zero when the spring is neither stretched nor compressed. And once it's compressed, it's going to push in the other way, back to the right to slow it down and stop at five. Then it is going to continue to push to the right, however, diminishing back down to um, no force is exerted, so an acceleration is zero, and then finally again back to one. When you look at these graphs, the initial uh, reaction might be to draw a diagonal line, but if you look at the position versus time, a diagonal line on a position versus time graph, that would indicate a constant velocity, where clearly here the velocity is constantly changing. So the only thing that can account for something like that is a cosine function. So you have a cosine function here, you have a negative sine function here, and you have a negative cosine function here.